Hey guys, it's Professor Sweeting here. So this week we're going to be discussing coloring problems. And these problems involve the coloring of various components of a graph. So components like vertices, edges, or if the graph is a planar graph, which is a type of graph that we'll discuss later, faces. So unlike the previous material, our study of coloring problems won't be driven by a particular real-world problem, right? So in the case of when we were looking at the study of Hamiltonian circuits, we were looking at the traveling salesman problem and the vacation planning problem. In the case of Euler circuits, that was done in the context of the postman problem and so on. So in this instance, we'll just be discussing these coloring problems, and as we go along, we'll talk about examples, right? So they won't be the main focus. So now, we aren't just interested in any coloring of these components. Rather, we're interested in what's known as a minimal coloring, right? So that is an assignment of color to each component of the graph so that no two adjacent components share the same color and which uses the fewest number of colors to do so. So this notion of adjacency will vary based on the component we're looking at. For example, we consider two vertices adjacent if an edge connects them, two edges adjacent if they share the same vertex, and as we'll see, two faces adjacent if they share an edge. So let's look at that. So in a graph, let's say we have something here, and we're coloring the vertices, and we're concerned with two vertices not sharing the same color, right? So if we've colored this vertex blue, I hope that's showing up, right? Then this notion of adjacency for the minimal coloring problem for vertices means that these two vertices can't be the same color because they're adjacent to this vertex, right? Because in the case of vertices, adjacency means that two vertices share an edge. So these two vertices share an edge. So for our minimal coloring, or our coloring of a graph, we can't have these two vertices have this, having the same color, okay? And in the case of edges, right, so this is perfectly fine because they're not adjacent. And, right, so these are adjacent, so they have a different color. But this is perfectly fine because these two vertices are not adjacent in this graph. So these are the types of colorings we're looking at, or what we're concerning ourselves with when we talk about components and adjacent components. Right, so in the case of edges now, right, say we had another graph here. Okay, so we color the edges when, in this case, and we have the two edges, right, are adjacent if they touch at a vertex, if they share the same vertex. So in this case, this edge shares this vertex with this edge, so it would need to be assigned a different color. Okay, so that's kind of what we mean by adjacency for these coloring problems with respect to the different components, right? Okay, it should be noted here that, so we'll talk about faces later. So it should be noted here that specific colors aren't what's important. So it doesn't matter if we used blue and black to label our components or pink and red. It's not even important that we're using colors. The essence of this problem is in the assignment of a label to each component from a set of labels such that no adjacent components share a label. So that is the essence of this minimal coloring problem for components. So these labels can be anything. However, when we use colors as labels, it just helps to make things a bit more familiar and inviting. So I should also mention that there are myriad graph coloring questions one can ask, aside from this question of finding a minimal coloring on these components. Such examples include oriented coloring for directed graphs, right? You have a coloring such that no, adjacent vertices that share, of one particular direction can share the same color. And also equitable coloring, that's another type of graph coloring question. So in this case, the number of each color used varies by at most one. So the total numbers of maybe this like pink used in a graph for whatever component doesn't differ from the number of blue colorings used in the graph, right, for that same component. However, the minimal coloring problems for adjacent components, right, which are the type that we'll be looking at and that I've mentioned, have the most wide and varying applications. So this is what we'll be focusing on. So we're going to start with the vertex coloring problem. So the vertex coloring problem. So I know this might have been a bit of a confused explanation because I was trying to handle all three cases at once, but we'll be looking at this minimal coloring problem for components, right, such that no adjacent components share the same color, right? We're going to be looking at each separately for each component. So hopefully things become clear when we talk in that more specific context. So the vertex coloring problem. This is the minimal coloring problem with respect to vertices. So that's the component in this case. That is to say, we want to find an assignment of a color to each component of a graph. And by component here I mean vertex. So in this case it's vertex. So we want to find an assignment of a color to each vertex of a graph so that no two vertices connected by an edge share the same color and which uses the fewest number of colors to do so. Right? So this minimal number of colors for a given graph has a special name. It's known as the chromatic number of that graph. So let's look at a few examples. Right? Okay, so say we had a graph that just had 4 vertices, right? And 3 edges. Okay? So I want you to pause the video, right? And think of what the chromatic number is of this graph. So what is the fewest number of colors needed to assign a color to each vertex of this graph, right? And have no two adjacent vertices share the same color. So adjacent meaning, right, two vertices are adjacent if they share an edge directly. So in this graph here, these two vertices are adjacent, while these two vertices are not adjacent because they do not share a direct edge. Okay, so I want you to think about that for a second. Okay, well, let's see. All right, so we necessarily have that these two vertices should have different colors. So let's say we colored this vertex like pink. That does not look pink because of the pencil bleeding in there. Let's see if I can make this look a little better. Not really. So let's draw that graph again. And let's make our vertices a little larger this time. So we'll do this. Okay. So these two vertices are adjacent and necessarily need to have different colors. Okay. So let's color this one pink. And then let's color this one blue here. Okay. Right. And this is not, I'm not going by any algorithm when I'm doing this. So we'll see that there is no general algorithm. So I'm just kind of experimenting, and we'll see if we can reason about our answer, or reasonably guess that our answer is correct in that it uses the minimal number of colors. Well, we can reuse pink here, right? Because it's not adjacent to this vertex. Okay, and then we can also reuse blue here because it's not adjacent to this vertex. It's only adjacent to this one, and they'll share different colors. And that is by far, I think it's easy to see in this case, that the chromatic number of this graph is then 2. You can't use fewer than 2 colors to color this graph such that all adjacent vertices have different colors, okay? So let's call this graph A. So chromatic number of graph A is 2. Oh, okay. All right, cool. All right, let's look at another graph and see what its chromatic number is, right? Or what the answer to the vertex coloring problem is of this graph, of another graph, graph B. All right, so let's do something a little similar. Okay. All right, let's see. Okay, so let's say we color this vertex here blue. So I'm just noodling around to see, you know, how few colors I can use and color this graph, and have adjacent vertices of different colors. All right, so we can color this blue, right? And it's connected to these two, right? So these two have to be different colors from this one, right? So if I make, but they're also connected to each other, so they have to be different colors from one another. Okay, so we need two other distinct colors at least to color these two. So let's use like a green, right, and then a pink. Okay, right, so that was necessary. So we at least need three colors, because if we colored one of these, these two need to be a different color from this one, but they're also connected, so that they need to be a different color from one another. So we at least needed three colors, and then we can reuse one of either pink or blue. Sorry if you're, if you might be colorblind. This might be a bit difficult to follow. I didn't think about that. So anyway, let me finish, and then I'll go back over and I'll discuss. We'll look back at these problems. So if you have color blindness difficulties, just give it a second, and we'll talk about chromatic numbers and this minimal coloring problem in a different way, right? And just kind of touch on its true essence. So we needed three colors for this graph B. So we say that the chromatic number of graph B is 3. Okay, so just kind of giving you an idea of what this looks like in an actual graph. All right, so let's go back here before coming back and talking about this in a different way, right? Okay, so, actually I already mentioned. So the essence of the problem is not that we're using colors. It's in the assignment of a label. I forgot I said this already. So when we were looking at colors for each of these vertices, we could have instead been talking about labels, right? So how many labels do we need? What are the minimum number of labels do we need so that we can assign a label to each of these vertices? So let's say A, B, right? And have the labels of two adjacent vertices be different, right? So this is the same. The idea of coloring and the idea of labeling, so that no two adjacent components, in this case vertices, for the vertex coloring problem, are the same. Okay, so in this case, this only needed two labels, A and B, right? So these aren't adjacent, so these can share the same label A. These aren't adjacent, so they can share the same label B, and everything is good, right? In this case, if we labeled this A, these need to be two different labels from this one, right? And they also need to be different from one another because they're adjacent themselves. And then, so we needed at least three colors for this kind of a configuration, and then we can just color this something that we've used before, right? To not use more colors than necessary. So we can use just as many colors or labels as there are vertices, right, for this problem. But that's not what's interesting. What's interesting is the fewest number, right? So, yeah. That's what we'll always have in mind. Okay. So, as is the case for other problems we've considered, there's no one algorithm that will produce the chromatic number for any given graph. However, in the case of graphs from a graph family, that is to say, a collection of graphs which share some structural pattern, for example, bipartite, cyclic, and complete graphs, we can sometimes reason their exact chromatic numbers or devise tailored algorithms for their solution. So let's look at some examples of this. So I mentioned three graph families here: bipartite, cyclic, and complete graphs. Right. So a bipartite graph we've looked at before in the context of Hamiltonian circuits. Bipartite graph. And what these things look like are two rows of vertices where the vertices, right, so a left row and a right row, where the vertices in the left row are connected by an edge to every other vertex in the right row. So vertices in the left row are connected to every vertex in the right row and vice versa, but no vertices in the left row are connected to one another via an edge, and no vertices in the right row are connected to one another via an edge. Right, so this is a bipartite graph, with 6 vertices. Another example of a bipartite graph is this right here. That's with 4 vertices, and we can do, unequal number of vertices on each side. This is also a bipartite graph. Okay, and let's try to reason what the chromatic number of such a graph is. Okay, well, if we can color, right? So we're trying to use as few colors or as few labels for these vertices as possible. We know that all the vertices in the left row have a different color, or are connected directly to one another via an edge, so they can, in theory, share the same color or label, and the same goes for all of the vertices in the right row. They too can share the same color or label. So let's say we had given, right? So we're trying to make most efficient use of colors or labels here, right? Minimal number of colors and labels to give to each vertex, right? So let's see if we can make do with just using 2, right? So if we took advantage of that observation that no vertices in the same row share an edge, or excuse me, in the same column. I don't know if I've been saying row or column. If I've been saying row, I mean column. Right, so let's give these labels A, give these labels B, right? So is this coloring valid? Is this coloring such that every 2 adjacent vertices have a different color? Let's see. Well, this vertex is adjacent, so every vertex in the left column is adjacent to every vertex in the right column. But if their labels or colors differ, right, then we're okay, and that is the case here, right? So the label / color of vertices in the right column, in the left column, differ from those in the right column, and vice versa. So this is a valid coloring. So the chromatic number of this particular bipartite graph is 2. Right? But the same argument holds for every other type of graph like this, right? So if all of these graphs have that same structure, where we have vertices in a left column and a right column, and that particular assignment of edges, then we can give them all the same kind of coloring or labeling, right, if you will, and have it be minimal. All right, so the bipartite graph family is one such graph family for which we know the chromatic number of each of its members. Okay, so all of these have chromatic number 2. Right, so that's just an example of where if we have a particular type of pattern appearing in a graph, then we can, know this property a priori, I think. Anyway, okay, let's look at another type of graph family, right? So I mentioned complete graphs. So we've seen complete graphs before, again, in our study of Hamiltonian circuits. So a complete graph, if you've forgotten, is just a graph where every vertex is connected to every other via a direct edge. So this is a complete graph on 4 vertices, and remember, a complete graph on 5 vertices looks something like this, and then on 3 vertices looks like this, right? So every vertex is connected directly to every other vertex via an edge, right? And so we can reason that if we color something here, right? Let's look at the complete graph on 4 vertices. If we color one of its vertices, right? Give it a label. Then we know that every other vertex has to have a different color than it. Okay, so no others can be blue. Right? So in particular, this vertex, or excuse me, or have this label. So in particular, this vertex can't have that same color / label. So we have to give it something different, right? And every other vertex is connected to both of these, right? So if we're choosing, say, picking another vertex to color, right? We can't reuse any of these two that we previously used, so we have to use another one, right? Okay, another color / label. And then for the next vertex, right, it's connected to all of the previous three that we've assigned a label / color to, so it has to be different as well. Okay? Right? And you can use the same argument for a complete graph on any number of vertices, right? If we assign one a color, if we start by assigning one vertex a color / label, right, and we're looking to assign the next vertex a color / label, it has to at least be different from the previous, right? And then once we've assigned that, once we assign the next one, the next vertex the next vertex a color / label, it's connected to the previous two directly by an edge, by definition of this graph being complete. So therefore it has to be previous, right? Have a different color / label than all of the previously assigned vertices, right? And so on. Okay. Okay. So what we can reason from this is that the chromatic number for a complete graph with n vertices is n. Okay, it's going to take just as many colors / labels, right, to assign to each vertex so that adjacent vertices it's going to take just as many color / labels as there are vertices to assign each vertex of a complete graph a color so that / label so that it's different from that of adjacent vertices in that graph. Yeah. Okay. That is like a mouthful to say. And the last graph family that I mentioned was cyclic graphs. So these just look like a cycle, right? So they just kind of, however many vertices you have, you kind of draw them around in a circle, and then you connect them on the outside via edges, right? So that's a cyclic graph on 4 vertices. This is a cyclic graph on 6 vertices, right? Cyclic graph on 3 vertices. Cyclic graph on 5 vertices. So it looks like how we've been drawing these complete graphs minus all of the edges on the inside. Okay, so let's try and reason about what the chromatic number is, or if we can reason about the chromatic numbers of elements of this family, right? So is there a pattern just in the chromatic numbers, just as there's a pattern for the appearance of these graphs? Well, let's see. Right, so if we start with something like this, right? So we know that this is complete graph. This one right here with 3 vertices, right? This belongs to both graph families. This kind of triangle-looking graph here. It's complete because every vertex is connected to every other vertex directly by an edge, and it's also cyclic because it has this kind of shape. All right. So we know that this requires 3 vertex / labels, or excuse me, 3 colors / labels, right, for the coloring. Okay. I apologize, if you do see the colors and labels that I'm not being consistent with their matching up here. But anyway, okay. And then what about for the case where we have a cyclic graph with 4 vertices? Okay, so let's start. We can choose a color for the first vertex. Then we know that the adjacent vertices to this one need to have a different color, and we can reuse the same for both of them. And let's also give the corresponding labels here. Alright, and then we can actually reuse the first color / label. So yeah, so we get the chromatic number of this one is 2, chromatic number of this one is 3, right? And let's maybe look at 5, and let's try to determine if there's a pattern here. So that's usually, with these kind of graph families, if you're trying to deduce some other pattern from their kind of appearance pattern, this is how you would go about doing it. You look at a few examples until you can kind of see what's going on, right? So let's do this. We're doing that here, right? So if we assign this one a color, right, / label, right, its adjacent ones need to have a different, at least one, they can share this, they have to have a different color / label. They can be the same, right? That kind of is efficient because we're minimizing the total number of colors that we'll use in the end. And then let's try maybe giving this one the color that we / label that we started with, right? And then it seems that we need another one. Okay, this can't be either blue or have label A, or be pink / have label B, right? So this has to be something entirely different. Okay, so the chromatic number for this graph was 3, this graph was 3, this graph was 2, right? And if we kind of follow this pattern, right? So let's look at the chromatic number for the cyclic graph with 6 vertices, right? These can be blue, pink, blue, pink, and we've managed to do a coloring, right, with only 2 colors here. So the chromatic number of this cyclic graph with 6 vertices is 2. So if we can kind of draw a pattern from what we've seen regarding chromatic numbers, the chromatic number for a cyclic graph with n vertices is 2 if n is odd, and 3 if n is odd, and 2 if n is even. So you can make your argument a little more rigorous, but this is just to illustrate that we can kind of know what the chromatic number is for a family of graphs based on some pattern that they share, right? So, but you can't know the chromatic number for any graph in general, right? And some graphs don't really fit a nice family. So you can have something really crazy like, I don't know, something like, we've seen plenty of crazy graphs in this class before, so I don't know. So something that really doesn't fit our, a nice structure, a nice pattern, okay? All right, so we're going to end this video by discussing a problem which can be modeled by a graph and solved via vertex coloring. Okay, so here's the problem. Say we have a list of equal length tasks we want to schedule, and for this list of tasks, we don't have any specified priority list or order requirement diagram. We only know which tasks can't be scheduled at the same time, right? Because maybe they share some resources. So how can we find out the minimum length of time it would take to complete all of these tasks, right? So this is the equivalent of finding the critical path length in an order requirement diagram for our usual scheduling problems, and is called the make span in this context, right? Okay, so if we create a graph, so that's the problem. So if we create a graph whose vertices are the tasks and edges connect vertices if the corresponding jobs can't be scheduled together, then the chromatic number of this graph will be the optimal scheduling time of all tasks. Right, so let's look at a few specific examples of this problem. Right. So here's a specific example. So say we had, 4 tasks, T1, T2, T3, and T4. And they all take the same amount of time to complete, right? Okay, and we know T1 can't be scheduled with T2, T3, T4, right? T2 can't be scheduled with T3, T4, and T3 can't be scheduled with T1. Okay. So let's create that graph. So we're trying to find out so none of these, it seems from this we can read that none of these tasks can be scheduled at the same time as one another, right? Okay. So we want to know but all these tasks take the same length of time, say 1 to complete, right? We don't know what that unit of time is, it doesn't really matter. But we want to know what the minimal amount of time it will take, what that minimal amount of time is, right, to complete all of these tasks. Okay, so this is, like I said, this can be solved via vertex coloring, right? So we create a graph with whose vertices are all of the tasks, and then we add edges between the vertices if the corresponding tasks can't be scheduled together, right? So in this case, none of the tasks can be scheduled together. So there's a vertex between every edge, right? And we've considered the chromatic number, right, of this graph. So the chromatic number of this graph will be the minimum amount of time it will take to complete all of these tasks, right? So this is a complete graph on 4 vertices, and we know that its chromatic number is therefore 4. It's going to take 4 different colors / labels to assign one color to each vertex such that each adjacent vertex in the graph has a different color, right? So we've seen this already. Okay? So that means it's going to take 4 time units, right? Since chromatic number of graph is 4, tasks will take 4 time units to complete. Right? So by complete, we mean complete all of them, right? Each task takes 1 time unit. And this makes sense, right? So if you have these 4 tasks and none of them can be scheduled at the same time, it doesn't matter how many processors you have to schedule these tasks, right? Okay? So we had 5 or something, right? Okay? So if we started processor 1 on task 1, because task 1 can't be scheduled with any of the other tasks, right? You can't have any other processor working on any of the other tasks while processor 1 is working on task 1. Right? And so when task 1 is complete, then we can work on another kind of another task. It doesn't really matter which one it is, so say T2, because this is not the usual type of scheduling problem where we had a dictated order or anything, right? Or a priority list for breaking ties. So it kind of, you can kind of think of it, as needing to have these tasks like stacked up in a row in your scheduling, right? If they can't be worked on at the same time. So the chromatic number will correspond to this total length. Okay, so let's look at another example, right? Where things are a little better, right? We do have some kind of, do have fewer restrictions, right, or conflicts between the tasks, right? So say task 1 can't be worked on at the same time as T2 and T3, and then task, let's see, 4 can't be worked on at the same time as task, let's say 2, okay? Right? So we need to figure out, and all of these tasks take the same length of time, say time unit 1 to complete, right? So we want to find out what is the minimum length of time it'll take to complete all of these tasks, right? So we set up the graph, right, for this problem, right, this graph model, where the vertices are the tasks, okay, T4, right? And then we connect the vertices of these graphs if the corresponding tasks cannot be worked on at the same time. So T1 can't be worked on at the same time as T2, T3. So that means there's an edge between the vertices corresponding to T1 and T2 and T1 and T3. And T4 can't be worked on at the same time as T2. That means there's an edge between T4 and T2, right? So we know what the chromatic number of this graph is. We looked at this earlier in this lecture, right? And it's 2, which we can find by just maybe coloring this blue, or that is just, or giving this a label A, also giving this a label A, right? So we can reuse that color, and then, so I'm not giving very rigorous arguments as to why this is the chromatic number. We're just kind of noodling our way along and kind of reasoning very lightly. But this chromatic number of this graph is 2. So that means the minimum length of time that these tasks can all be completed in without violating these conditions is 2, right? And so how can we see that? Well, it's T1. So that chromatic number gives us the information. What I'm trying to do is come at the problem from another angle to see that. So this is a far more elegant solution, right? This notion of, transferring this information into a graph and then finding the chromatic number, than it is looking at it this kind of way with, processors and scheduling them, on them, right? So if 2 vertices can have the same color, that means that they can be worked on at the same time, right? So you can have maybe T1 and T4 going, right? Okay, but not T2 and T3, okay? Because T1 would conflict with T2 or T3, okay? And also T4 would conflict with T2. And then once they're done, you can then work on T2 and T3, right? Because there's no conflict between them. So just the colors then represent conflicts. So in that graph that corresponds to this problem, right? And that includes this information of what can and cannot be worked on at the same, like which tasks can and cannot be worked on at the same time. 2 vertices, right? If the vertices represent the tasks, can be worked on at the same time if they can be assigned the same color. So that's just kind of how it relates. All right. So if you have any more questions about that, you could just feel free to ask me on the discussion board. Okay, so in the next video, so that concludes our discussion of the vertex coloring problem. So in the next video, we'll discuss the edge coloring problem, which is the analog for where the components are, for edges in a graph. And we're going to look at examples of graph families with known solutions for the edge coloring problem, and then some of the applications of the edge coloring problem. All right, bye.